So what I'm going to talk about is this paper that I have recently written with my collaborator Nikola Paunkovic about the definite and superposed causal orders and quantum gravity and this sort of stuff that is a hot topic apparently. So it is still not working.
Are you pressing the down button?
I'm pressing both of them interchangeably and neither of them is. Please. Maybe it's turned off.
The battery, it was working before. I don't know.
The battery used to work, but it is not working.
Oh, no. Okay, there is an on-off button.
Ah, it was turned off. Okay, so it's okay. Technology has this on and off thing that is computer science. Okay, so yes. There is it was turned off. Not really. When you turn it on, it works better. So. So what am I going to talk about? So I'll give a short introduction into graphs, quantum circuits, space-time, causality, and all that notions. I will mention the notion of a quantum switch with several types of realisations that we will discuss in detail. I will demonstrate an observable which distinguishes between these realisations, which is basically the key point of the lecture. And I will give some implications for the relational view of physics, which is something that I think that everybody in the audience is interested in here. So, let me begin by saying that there is a terminological clash between the relativity community and information theory community. And there are some problems, so I want to make a sharp distinction in terminology so that we understand each other better. Now, the notion of an event is, in relativity, it is a space-time point. Okay, so it is a point on a space-time manifold. If you open a book in special relativity that says what is an event, it is a point in R4, right? That is an event. And in information theory, this is like a very old definition. This is like 100 years old definition. Now, information theory, as I understand it, and I'm not an expert in this, so this is not my area, but as far as I understand it, an event is basically an interaction between a physical system and an instrument, right? So it is something that happens in a gate in a particular circuit in a quantum information description. So in order to distinguish these two things, I will call the first one the manifold event or M event, and the other one is a circuit event or the C event, right? So what I'm going to be discussing is that these things are not the same, okay? And one should be clearly distinguishing what these things are. Now, the second thing is the causal order. So in relativity, when somebody says causal order, they mean the relation of partial order defined by a light cone structure on a space-time manifold, if such a structure exists on a manifold. Usually the light cone structure is induced by the metric, but that is... And in information theory, the causal order is a different relation of partial order, which is defined by basically oriented links between the gates in this circuit diagram. So a circuit diagram is an acyclic ordered graph, and basically it has a partial order relation inside it, natural. And this partial order relation tells you like which gate happens first and which gate happens afterwards. So the morale of the lecture is to demonstrate that these things are not the same thing. They are both observable, and they are not equivalent. So one should be very, very careful when one talks about causal order and which causal order. I put the scare quotes here because, I mean, the notion of causal order in both in relativity and information theory is a bit of a misnomer because we are not really talking about causes and effects. we are talking about the time ordering of events, right? Regardless of whether they are causally connected, in a causal relation in this philosophical sense, that one is causing is the cause of the other, right? So in relativity, this is somehow sort of equivalent because relativity is sort of deterministic theory, and the deterministic theory causes everything that happens before is a cause for everything. I mean, it's a definition of what the cause is, an effect. But in information theory, we don't really have, usually we don't have a deterministic description. We do not need to have a deterministic. I mean, quantum physics is not deterministic. So the word cause and effect are really not. But anyway, this is somehow a sort of a traditional terminology, despite the fact that. But what is important is that we are talking about the time ordering or partial order relations. So these two partial order relations are what I'm going to focus on in the rest of the talk. So Giulio has this morning given an excellent lecture from the information theoretical point of view about what is the quantum switch. Also, Cyril has given the process matrix description of it. Giulio Rubinho will talk about the experimental context in which this thing happens. And for a guy in relativity, what is left is to give a space-time description of the whole thing, right? So I will be very, very brief and so the point is that this is a typical thing that happens when you do the quantum switch. This is one of the possible things that can happen. So this is a space-time diagram, a proper space-time diagram. I'm paying attention that light cones are at 45-degree angles here, and so on, so you can read it. Now time goes into horizontal direction because the slides are in landscape mode, so I couldn't really. This is. I'm sorry for that, but. Okay, so what happens here in this picture? Okay, so we have some initial point like where sort of a beam splitter or some device that puts a certain particle into a superposition of two different trajectories. One trajectory is driving it towards Bob, and the other one towards Alice. So once it reaches Alice. This is the world line of Alice's laboratory. This is the world line of Bob's laboratory. So once the particle reaches Alice, Alice performs an operation, U, on the particle. Typically, I will discuss the unitary operations, but you can put whatever you want here. But unitary operations are mostly the most easy to discuss. So there is a unitary operation U that Alice does here. And then she passes on the particle on its way, so it continues on going to the Bob's lab. And then Bob performs an operation V on the particle, and then he passes it on to the final state where we have an instrument which basically can measure all sorts of stuff on the particle. And in the red history, the same thing happens. It just happens in the other way around. Like, so the particle first reaches Bob. Bob performs the operation V, then it sends it to Alice. Alice performs the operation U, and then it sends it to the instrument. So basically, we have the switched order of operations. In one case, we have a UV operations, and the other one we have VU operations. And we have a particle which is in a superposition of these two histories. And the point is that these two histories interfere, so you can measure the interference here at the end. Like that's the main issue. So this is something that we call, Nicola and I call the 4-event process. Why is it a 4-event? Because we have 4 space-time points here that are in play. So what are the actual properties of the whole thing? So it has 4 relevant manifold events, A, B, A prime, and B prime. But it has only 2 circuit events. Only 2 operations are being performed. Either the operation U is being performed at A or at A prime, and the operation V, which is performed either here or here at B or B prime. So from the point of view of information theory, the causal order, or actually the relationship of ordering of the gates, is not well defined for this process, because, well, it is in a superposition of u being first and v being first, right? So in the blue history, u happens before v, and in the red history, v happens before u. So given quantum superposition of these two, this is not a well-defined partial order relation, right? Now, on the other hand, the causal order of space-time events, like the relativity causal order over a manifold, is well defined because A prime and B prime both happen after A, so they are in the light cone, in the future pointing light cone of A, and they are both also in the future pointing light cone of B. So yes.
What do you say that U is happening at either A or A prime? I mean, it's happening both at A and A prime, just on different branches.
Well, okay, so I will explain in what sense do I mean this. I mean, this is like an or and thing, right? So of course, it happens in each branch, it happens only once. So you can ask, after the experiment, you can ask Alice and Bob, for example, you can ask Alice, how many times did you interact with the particle? And she said, I will interacted once. She would not know whether it was this point or this point because, you know, she's not she does not have the which way information that would destroy the interference. But she does know that she interacted once. She can count the number of interactions with the particle. So in a sense, there are only two events, two circuit gates that are being applied here. One for Alice and one for Bob. The issue is that these two are delocalized in time, right? So from that point of view, we have something funny going on here, right? Okay. So so far so good. I mean, there is nothing spectacular going on here. I mean, there is, aside from the non-regular notion of quantum superposition and such stuff, this is all regular physics. Now, as you know, the notion of in quantum information theory community, the main keyword of everything is the notion of a resource. So everything is considered as a resource. So how can we be more optimal in using our resources to do this or that? Like, how can we be more resource efficient in a sense? So one way to be more, the one question one can ask when we're studying this is, can we be more efficient? Can we do this process? Can we perform this process not using 4 space-time events, but using less than 4, right? So that is a natural question one can ask, and especially in light of the fact that you know, 2 circuit events are happening, but somehow you need 4 space-time points for those 2 circuit events. So this is somehow, you know, there is a discord here, in a sense, and this is especially related to the notion of relational approach to physics, in which, I mean, the notion, this is something I missed to comment on. The motivation for this definition of an event in informational theoretical way, it has also its history in the context of relational approach to physics, where you discuss, you know, you say that an event is something where is a point in space-time, basically, where some physics happens, you know, where something happens. A space-time event, a space-time point in which nothing happens, you know, does not contain any information as such. So it does not really part of your description of your relational description of the world. So in this sense, in a relational point of view, this information theory definition is more natural than the traditional space-time definition. But then you run into problems because you want to describe, if you want to describe physics relationally, you have 2 events in the sense of the circuit, 2 interactions, two places. I mean, two interactions between Alice and the particle and Bob and the particle, and yet for those 2 interactions you need 4 points in space-time. That's not good. I mean, that's kind of problematic. So why is this happening, and how can we improve on that? So the natural way to improve is to say, yeah, well, we can, we can identify these points B and B prime, put them somewhere in the middle, and just slightly modify the process so that we have one event less, right? So we have three space-time events, three manifold events, by identifying the two space-time points. So we slightly modify the graph. This is all still completely under the on the inside of the light cones, the appropriate light cones. There are no problems here of any kind. And basically, we are saying the same story that is happening. Only now, you know, the event of interaction, the C event of interaction of Bob and the particle corresponds to a single space-time event. However, Alice is still using two space-time points for her interaction. And the properties of this three-event diagram are similar. We have three manifold events. We have two circuit events. The causal order of circuit events is still in a superposition of two opposite time orderings. And the causal order of manifold events is still completely well defined because we know what happens before, what happens afterwards. Now the question is, can we do even better than that? Like, can we identify even these 2 points, which would be something that we would want to do from a relational point of view and also from resource conserving point of view? Now that would be a 2-event process. So we want to identify both Bob's space-time events and Alice's space-time events. Now this is not possible on a classical space-time manifold. Let me show you why. Because if you move A prime to coincide with A, you will have in the red trajectory the particle will propagate backwards in time, which is a problem. If you move A to coincide with A prime, you will have a backward time propagation for the particle in the blue history. While if you move them both halfway, you will have a superluminal propagation of the particle. So it is either backwards in time or superluminal, and both options are basically not physical. So this is a problem. This kind of identification of both B and B prime and A prime somehow is not consistent with the causal order that is generated by the Minkowski metric in Minkowski spacetime. So, however, this is arguably possible to do within the framework of quantum gravity by creating a region of spacetime where we have a superposition of two different spacetime metrics. And this is called the gravitational switch. And the order of events is as before, a superposition of U and V, U before V and V before U. While now we have also a superposition of spacetime. Actually, let me show you the picture. This is what it looks like, right? A picture is 1,000 words, right? So what do we have here? So we have a spacetime region. So this is spacetime, curved spacetime in some way, quantum gravity spacetime. So we have on the outside of this yellow blob, we have a metric, so to speak, in a sharp state, right? So the metric is a quantum operator, and it has a well-defined value on the outside of the blob. However, on the inside of the blob in the yellow region, the metric is in a superposed state of having this value and having that value, basically two different superposed states, each corresponding to either red or blue history of the particle. Now, of course, the particle gets beam splitted into the blue and red history as it enters the yellow region. But this also happens for Alice and Bob and for anything basically that enters or exits. So this whole three-dimensional hypersurface, this boundary region, acts as one big beam splitter for everything that, it acts as this is field theory. So it acts as an infinite sequence of beam splitters, one for every space-time point here. So in a sense, this is a boundary condition. Field theory is
why in this picture at A and B the splitting is Like,
Sorry, what, please?
is it possible that the red and blue history at A, for instance, is like that A actually happens in two different points?
It is, certainly. But I'm interested in the case where these points are really identical. So A is 1 point and B is 1 point. If I split them, I will return to this framework, which we have already, which is not interesting. What is interesting is to have only two space-time events corresponding to two operations of the gates.
But
So
there are different histories of space-time. What do you mean?
sorry.
There are different histories of space-time. Different.
Yes, there is a superposition of the metrics here. So now, okay, I should keep this clear. In this model, I mean, quantum gravity you can do all sorts of stuff. In this model of quantum gravity, what is quantized is the gravitational field living on a classical space-time manifold. Okay, so the notion of a point is well defined, and the notion of the metric as a field which maps the point into the tensor algebra is an operator which can be in a superposed states. So the notion of a point, when I draw this diagram, every point here is a well-defined point. So it has, despite the fact that metric is in a superposition, when I draw a point here, it is a 1 point on the classical manifold. It has nothing to do with the quantization.
Gravitational states will not evolve in this case.
Sorry?
Gravitational states will be fixed.
No, evolves. Well, this is time evolution. This is a four-dimension. This is the space-time. It's the history.
Yeah, but the operator will evolve, right? But
Of course it will.
because you said that
No, the evolution is described by basically slicing this diagram into hypersurfaces and looking what happens at every hypersurface. And of course, there will be evolution. If you slice it here and if you slice it there, you will have different values for all operators.
Must have been a bad chair. I didn't signal. Now it's 7 minutes.
7 minutes till the end.
Sorry. No, sorry. 17. sorry. Yes.
17.
17.
So I have 17 minutes left.
Am I right?
Including questions?
Yes.
I didn't see when
So we started at 4.
Yes, 16 minutes including questions.
We have 17 minutes.
Right. Okay. So
Marko, so are you envisaging this as perturbative quantum gravity or linear
no, this
quantum
is something
gravity?
that can be realized, for example, in perturbative quantum gravity, or for example, in asymptotic safety. These are the theories which usually discuss quantum metric over a classical space-time manifold. I mean, it depends. This is model dependent. The question whether you can realize this kind of a diagram in a given theory of quantum gravity is an open question. Some will, some will not.
But is it fair to say that what you have in mind, I mean, it's sufficient to have two classical metrics and you put them in superposition?
Yes, but they are not both. I mean, you should be careful when you say classical. Yes, well, 2G mu news. Yes, that's basically what I'm doing here. But the point is that the whole argument in physics, in relativity. So this is the boundary condition for the metric. So if we specify the metric on the outside, the question of what is the metric on the inside region is a boundary condition for Einstein's equations. So if you want to solve Einstein's equations, there is a unique metric on the inside up to diffeomorphism symmetry, which is a solution of the Einstein's equations. So if you want to have two different metrics in the compact region, one of them must not be a solution of Einstein's equation. So you have an on-shell and an off-shell solution, or two off-shell configurations.
Well, why do you want them to be the same outside the region?
Well, this is, I mean, you can discuss non-compact cases, but then you don't.
That's not true. You can have some other matter in quantum superposition and give rise to the two different metrics.
Well, yes, but I didn't want to do. I mean, I wanted to limit myself for. I mean, certainly, if you add more matter fields, you can. Yeah. Of course, you can do that. Yes, but it's a more complicated situation. This one is sort of right. So basically, what is happening here is basically a naive picture of how would you do something like quantum switch. How would you realize a quantum switch using only two space-time events in this kind of setup? And if you remember, the causal order of the two gates is still in the superposition. We have only two manifold events and two circuit events, and now we have the causal order of manifold events also in the superposition, because A happens before B with respect to the causal order that is generated by the metric G, and the opposite with respect to the other metric, which is in the superposition. So this is basically what is going on. And now the main question is there a way to distinguish the two-event quantum switch, not specifically the gravitational switch, but is there a way to count the number of space-time events that we are using? So you can imagine a quantum switch being implemented in a black box, and you have some input, some output. The particle gets in, gets out, and you want to ask, does the black box realize this kind of a process, or does it realize this kind of a process? So the question is, can we count the number of space-time points which are being used here? And this is where the plot thickens. So operationally, the question is, can we distinguish manifold events A from A prime and B from B prime? So in the paper that was a famous paper from 2015, where the first experimental setup of a quantum switch, optical quantum switch, has been realized, there is this statement in the discussion which says that, of course, we can interpret this as four space-time events with the determined causal order, but any attempt to physically distinguish these events would reveal the which way information and thus destroy the interference. And the fact that we do see the interference in the experiment means that there is no information that can distinguish the A from A prime and B from B prime. So basically, the four causally ordered space-time events cannot be given an operational meaning. So this is the point. This is important from the point of view of relational physics, because it says that you cannot really observe an event in which nothing happens. I mean, it's sort of complicated to discuss. There is no operational way to distinguish this. However, I have to say that this was a sort of a misleading statement, because Nicola and I have sort of managed to construct an observable which directly contradicts this. So there is a way to distinguish manifold events without providing the which way information. And the reason why we were even looking at this is the fact that the individual space-time points are not observable in relativity because of the diffeomorphism invariance. So you don't know which point. The diffeomorphism symmetry basically permutes the points on the manifold, and you don't know if you're looking at this point or that point in the manifold, unless there is something else happening at that point so that you can distinguish them. However, if you know that 2 points are different in a given coordinate system, they are going to remain being different in all other coordinate systems, or under the action of all diffeomorphisms, because diffeomorphisms are invertible transformations. They cannot map 2 points into 1 point, and something like that. So this is a topological property. This is called so-called Hausdorff separability. I don't know if you remember. So we have 2 points. So you can put a neighborhood, a topological neighborhood, an open set around 1 point and another set another other point, and you say the 2 points are different from each other if the 2 neighborhoods do not intersect. Right? So that is the Hausdorff separability. And this is a property of topology, right? So this is something that is being respected by diffeomorphisms. And this is a diffeomorphism invariant property, the distinctiveness. So one cannot identify a space-time point, but one certainly can distinguish between 2 of them. That is an observable. That is something that can exist in principle. So Nicola and I went to look for an observable that would do precisely that, basically. So how does one do that? Well, basically, we introduce a third party to this game, a friend of Alice and Bob. And we asked for the following protocol. So we ask Alice and Bob, whenever they interact with the particle, they interact with the particle as before, but as soon as they interact, they also, in addition to that, they shoot a photon towards the friend. Okay? Bob does the same thing as Alice. So basically, whenever the interaction happens, there is a photon reaching friend. So we have 2 photons reaching the friend in the red history and 2 photons reaching the friend in the blue history. So the friend gets entangled with the particle because this is in superposition. Now, as Carlo explained in the previous lecture, you have to understand the friend as a quantum system. So this is not a classical laboratory. This is something that that is a part of your quantum description. So the friend gets entangled. And then, sorry, no, I'm going into the wrong, yes, so in the gravitational case, you do the same thing. Alice and Bob shoot the photon whenever they interact with the particle, but and these photons basically have 2 different trajectories in the 2 superposed geometries, but they get recombined here at the boundary. And the friend always sees precisely 2 photons reaching him, regardless of what happens, what history this corresponds to, right? So in a sense, the friend is sort of separated. He's in a product state between these 2 geometries. So this is the setup. So the friend can find himself, the wave function of the friend can be in 3 distinct states. This is one state in which basically the proper time between the reception of these photons is always the same, and the other 2 states in which the proper time between the reception of the photons is as in the red trajectory or as in the blue trajectory, blue history. So basic.
So the photons are the same or different frequencies?
The photons can have different. So Alice sends a frequency 1 photon, and the Bob says, so this is dashed this is dashed photon, this is dotted photon. So the Alice's photon is distinguishable from Bob's photon. That's the point. I mean, they can be identical if you want, but really there is no. I mean, it's you're allowed to distinguish them. So how does friend perform his measurement? What is the observable that we're talking about? So basically, okay, as I said, there are 3 states in which friend can find himself in.
Matrix, you were assuming, I missed that before. You were assuming that the 2 matrices inside are equivalent to one another?
Yes.
They're related by diffeomorphism inside?
No, they are not related by diffeomorphism. They're physically different.
Physically different.
Yes,
so
yes,
why the combined?
Because I wanted to recombine. I mean, this is the situation that realizes. I mean, if I want to have.
I see. So you're now assuming also that this happens.
Yes. So this is the part of the assumption. Okay. Because I want to see. I want to have a witness for the fact that there are only 2 space-time events that are happening here, as opposed to more of them. Right?
But how we can be sure that the dashed line are recombined? Because this friend just see the outcome.
Right. So this is, you know, the how do you call it? This blissful curse of field theory. You know, so field theory is beautiful because we have, you know, infinite number of degrees of freedom to play with, but it is also a curse because we have boundary conditions to take care of. You know, so. You can understand this hypersurface, this boundary, as a sequence of gates. So at every point on every space-time point on the boundary, there is a gate which does the Hadamard operation basically, and at this point, 2 photons enter the gate, and you choose the operation that you do at the gate so that it recombines them, and you do the same thing for the gate that sits here. You have an infinite number of gates here on the boundary. So you can choose this to happen, right? So to arrange for this set. So there is no, in principle, there is no issue. Yes.
So is your space-time region, the two metrics that you choose, your off-shell metrics, that needs to be fine-tuned with the trajectory of your friends? Is that correct?
Oh yes, yes. This whole thing is very, very fine-tuned. So you need to make precise, you need to have the a priori knowledge of what geometries are, what are the trajectories, what are the in which directions the Alice and Bob will shoot out the photons. Everything needs to be very, very precisely, prescribed beforehand. So this is a very special thing. I don't know if this thing exists, if it can be realized in nature, or what would be the quantum gravity model that would realize this. But the question is, if it does exist, I want to identify it. So that's what.
But the gravitational quantum switch, just last paper does that. If you add the friend on the side, what is the issue?
Okay, the paper by Chaslov and Magdalena and others is of different type. It is not localized in space-time.
Yeah, that's what I was saying.
Because
I don't understand why you want this to be localized. I think.
Well, because I want the friend to be on the outside of this block. So I don't want the friend to be in a superposed state of two different trajectories, right? This is the reason, basically. But you certainly can discuss the gravitational switch in which these two boundaries extend to spatial infinity, so that you have like. But boundary is a boundary. It is going to exist even in a spatial infinity. I mean, spatial infinity is just diffeomorphism away. So you can always draw it in a compact form. Okay, so let me speed up a little bit. So what does the friend actually measure? He can be in these three states, and he's measuring so-called dichotomic photon non-demolition orthogonal observable. This is a mouthful. So if the friend is in the state where he is in the superposition of this 4-event switch, right? So if he is in either the state, he's either correlated with the red photons or with the blue photons. He wants to get the outcome of the measurement of the measurement observable to be 1. So this is a projector on the red photons. This is a projector on the blue photons. And if he is in this state where the two photons are available only, then he makes a projection onto with the outcome 0. So basically, this whole thing is a projector to these two to the subspace spanned by these two vectors, while this one is in the kernel. So what happens in the 2-event case? In the 2-event case, the total state of the particle and the photons and the friend is basically a product state. So Bob is in this kernel of this observable. He gets the result 0, and he does so without disturbing the superposition of the particle. The particle is because they're in the product state, so there nothing funny happens. Now in the 4-event case, the friend gets correlated with the red and blue histories of the particle, right? And you can rewrite this in this form, like R plus B and R minus B combined with these two basis vectors for this is a 45-degree rotation in the space of friend and the particle. This is just linear algebra. This is an identity. And when Bob performs the measurement, these projectors are going to project, are going to act on one of these states, and he will obtain the result 1 for M. And once he does that, once he obtains the result 1, then he can perform the quantum erasing procedure by additional measuring of the two photons in this basis. So basically, he projects either to this state or to this state, and he gets this thing for the superposed state for the state of the particle. So if he knows the outcome of the measurement of M to be equal to 1, and if he knows the outcome of this of the measurement of this observable, he can post-select the plus state and recover the R plus B superposition of the state of the particle. and therefore also not disturb the superposition of the particle. So ultimately, what the friend does is to obtain a single bit of information, which is 0 if he is working with the 2-event process, or 1 if he is working with the 4-event process. And this bit of information does not reveal in itself the which way information.
So why the quote is wrong then?
So the quote is wrong because this is an observable that the quote says does not exist. So any attempt to physically distinguish the two, yes, would reveal a which way information. So we have managed to physically distinguish these 4 space-time events without revealing which way information. So basically that is the problem that I have. I mean, we can debate what is the actual statement here, and this is not really important. This is like a motivational statement. I don't want to go as far and say that this is exactly contradicting the
So
statement.
the which way information cannot be revealed, but whether it's a 4-event or
This
2
is
event
different
can be
thing.
revealed.
No,
Is that
but
the
which
case?
to physically distinguish the two. One thing is to distinguish between 4 and 2 events. This is what your observable can do.
Right. Yes.
Can you read out of the observable whether A was performed before or after B?
No.
No, because the time when a photon arrives will reveal then the which path information.
Precisely.
Okay, so that's the statement was about that. That A
Okay,
cannot.
if you say that any attempt is to the
photon-
time, if you want to distinguish the 2 times, yes,
At
I
which
agree.
a photon can pass through a gate.
Yes,
Let's
I
say gate A or
agree.
gate B.
Okay, so technically this is correct. Yes, but
The
still,
point of what you're saying is that there is a way to distinguish whether there are 2 points or 4 points.
precisely, yes. So I can. So the point that
These implementations are physically different.
yes. So what I want to say is that in addition to sorry, I'm going the wrong way. In addition to counting the number of the gates that are the gate events that are happening, the C events, I can also count the number of manifold events. That is also can be counted, and you can clearly see that you have 2 gate events corresponding to 4 M events and this kind of stuff. So that is the basic, the main point. So this is what friend does. Oh, where was I? Okay, so a few comments at the end. I'm finishing. So I already said that. So the C events can be counted by Alice and Bob, and the friend can count basically the M events. So you can give an operational meaning to M events, even without despite the fact that physics is not happening, that nothing is happening at some of them, right? So basically, the moral of the story is that the space-time causality cannot be identified with the order of gate operations in a quantum circuit. You have to really be careful when you are doing this, when you are making these kind of identifications. And the quantum superpositions of causal orders, where I mean causal order in the space-time context, can be discussed only in quantum gravity, if at all. I mean, you cannot do this, right? So you can have this. You can have a superposition of 2 space-time causal orders if you have a superposition of 2 different metrics. But in a classical space-time, you really have a unique causal order, space-time causal order always. So there is nothing to.
Can I?
Yes.
So would you go as far as say that if you witness the realization of the quantum switch and on top of that you witness that you have only 2 events, would that witness non-classicality of space-time?
Well, that is basically what I'm suggesting here.
But
That
do
you
think
need to
you'll
have a
prove
quantum gravity model in order
that? Did
to
you
implement
prove?
this kind of behavior.
That's
but,
what I guessed too. But do you have a proof? That's what I'm.
Well, not proof is in a rigorous, proof, because this is dependent. Quantum gravity is a vague thing. It's ephemeral thing. So it is model dependent. So in certain formulations of quantum gravity, you can do this. In other formulations, you cannot. And this is kind of a vague thing so to give you a a mathematically rigorous proof is a tricky thing. but maybe it can be done. I mean, we can work on that. We can discuss that. So as a final point, I would like to give a more general reflection on the idea of relational physics. We have heard in one of in your talk previously, there was this statement that I sort of jumped on, that individual points on the manifold cannot be identified, and therefore they sort of do not exist. So I pushed back on that because you cannot. It is true that you cannot identify individual points, but there are many properties that they have that can be observed, that are observable. And if you want to describe a relational, if you want to describe nature in a relational way, which is something that I do like and do favor, you have to be very careful when you're discussing the structure of space-time. So you cannot just throw it away in a sense. Because the number of dimensions of space-time is an invariant, and it is an observable. Its topology is an invariant and observable. Its causal structure, if it exists, is also classically an invariant and observable. And the distinguishability, the mutual distinguishability between any 2 points is also an invariant and observable. So if you have basically two ways forward. You can either postulate all these invariants in your theory, and in that sense you have a space-time as an ontological object that is postulated to exist in your theory. It is not a relational thing, right? Or you can aim to derive the values of all these observables from some simpler first principles of your theory, which would be like the emergent space-time scenario. But then, you really have to have some simpler relational first principles, in the sense that they are not equivalent to these postulates in a different language. So there needs to be a one-way implication from your relational first principles to the. Okay, this can be formulated precisely in a logically rigorous way, and basically, I don't know of any model which has managed to determine that space-time has 4 dimensions. So there are no models so far that are fully relational in this sense. And basically, this is a very hard problem. In string theory, they have attempted to give, without even wanting to be relational, they attempted to give a calculation for the space-time dimensions. They obtained the wrong number. So this is, in a sense, this is a very hard problem. So if you want to do physics relationally, you either have to postulate that the space-time exists physically, or if you don't want to do that, you'd better give me very good reasons how to derive all of its properties from some ab initio theory.
Before even I look back and see who's asked question, I think we should actually contain the time. I know that these are kind of pretty controversial and exciting topics, but just so that you know, we are already 10 minutes late with respect to the schedule of this own talk. Not without counting what we had before.
The question would not be controversial.
So okay, I would limit maybe to these 2 questions.
Let me just say that I will be here until the end of the conference, so we can talk even.
What I was thinking, that pretty much many of the things that we have done today do include a lot of discussion and stuff. We may want to actually have a session outside of the program where we sit or come to this room and discuss the whiteboard freely for those who are interested. But I would limit here really to the delivery of the results that we want to talk about.
I'm not sure we can go on, with Julia's talk now, actually, because, we're supposed to end the session 10 minutes ago.
Yeah. Well, to end this talk 10 minutes ago, not the
It's
session. We were already late because of our earlier. I mean, it's still fine for me. 1 hour lunch. Yes. So for me, it wouldn't be too strange that we have lunch from 1 to 2. 1 hour lunch and then starting looks fine to me.
We'll start a bit later.
Also, we are kind of overfed all the time, so it's like feed.
Okay.
It's more a clarification question. And usually we think about these causal structures in terms of the columns of process matrices, where you have this causal structure and then you embed or insert some local operations. Now, this gravitational switch, as you said, is very fine-tuned on the local operations. So if I choose to do any other local operation instead of the one for which you fitted exactly the trajectories and everything, they will not anymore fit. So this seems to be not symmetry, which is not wrong. I'm just trying to distinguish.
The local operation that is being done here by Alice and by Bob is sort of a unitary, the polarization of the particle or something, change of the polarization. This does not change its space-time trajectory. So I can choose a different polarization here and a different polarization here and still get the same thing, right? So this is the operation that Alice and Bob can do. They can do in the space of internal symmetries of the particle, so that it has nothing to do with its space-time trajectory.
Somehow these degrees of freedom really do not influence.
Well, they may or they may not, depends on which degree. If these degrees of freedom couple to gravity, then they will change the trajectory. But if they do not couple to gravity, then they will not change the overall. Yeah.
It's basically a short comment. I think I agree with everything you said. I find
Thank you.
convincing.
Okay.
I would say it slightly different. You insisted that in order to run this picture, this particular one you have of the, you're thinking in terms of a fixed space-time manifold on which there are two different.
Yes.
It seems to me that the entire story you gave remains perfectly consistent and, at least to my eyes, more convincing if you don't think about that. Because here what you have is two different branches.
Okay.
A priori, two different branches. You have A and B on the red branch and A and B on the blue branch. There is no a priori way of identifying point. There is no meaning of identifying point. But you're saying, wait a moment, there's no a priori way, but there are concrete ways of doing that. So I can identify points physically. And you're given a case in which you say, let me give a physical definition of the point A in each branch and a physical by introducing your friends and see what your friend sees. And you say, look, now I have a procedure for saying which one is the same point, because this is a point seen by friend.
Yes.
And under this procedure, I know that A in the blue is the same as A in the red, and B in the blue is the same.
Yes, exactly.
So that's, I think, what is going on. And this is convincing without the need of having this carpet of
Underlying manifold. Yes, yes. You're right.
The other way is not even convincing, because then you have the background causal structure, and if you were to do this in linearized
Causal structure is in the topological
If
manifold.
you were to do this in like perturbative quantum gravity, then you would have the causal structure of the background time.
The perturbative, yes.
And then you would still, I think then you wouldn't actually be able to run this.
Right. This wouldn't work in perturbative.
Exactly. So that's what I think.
Yeah, but as far as Carlos' comment goes, it's you're correct. You can use this observable that I have constructed as a form of a definition of what a manifold point is, even if you do not have the background manifold structure, right? Okay, certainly you can do that. You can think of it like that. I agree. But it's just that this was more convincing from the presentation point of view, because you expect people in the audience to ask, how do you know that this is 1 point and not 2 points and this kind of thing? Before I introduce the observable, I cannot really. So this is more of a pedagogical thing. But you can put it the other way around once you know the observable.
But in that case, you could always come up with a second friend.
Sorry guys, I think it's the moment to move to the next topic.
No, all the friends which are lying on the outside of here will always see only 2 photons. You can put his trajectory anywhere.
Wait. So there are infinitely many things we can discuss on these things, and we have done this for years. So let's keep this to the kind of delivery of the contents, and let's leave the debate for the moment outside the talks. So let's thank again Marko.